Hi class, welcome to the next section. Today we're going to talk about chapter 1.8, which is logarithmic functions. So again, we're still reviewing a lot of the pre-calculus algebra material. So hopefully you remember that logarithms and exponential functions are inverses. Okay, so a lot of times when we want to solve an exponential equation, we have to take logarithms in order to solve it. So the way that I like to think about it is that we start off in exponents. A lot of times we have to go into logarithms and then back into exponential form. Or maybe we have a logarithmic equation and then we have to go into exponential form in order to solve it. So a lot of times when we kind of hit a brick wall, we can't move any further in our arithmetic and our calculations, we have to use the inverse function in order to finish solving our equations. So again, right, to start, logarithms are inverse functions for exponential functions. If I have a function that is a base raised to a power, and the input to that function is the power, right, an exponential function, then I can take the inverse of that function, or the log of that function, as log base b of x. So one way to remember is this exponential function has a base of b, and the way I say my log function is log base b of x. Okay, and so what happens then is what I get out here turns into the input here, right? And the input for this exponential function is the value I'll get out when I plug in this output. So they're inverses, so they go back and forth, right? And the same is true if I think about it the other way. If my function is log base b of x, then the inverse function is b of x, b to the power of x. When we have a base of e, the natural logarithm, then or the natural base, I should say, then our log is the natural logarithm, or ln of x. Okay. If there is no base present, like in this form, you don't see anything in the bottom, there's no 5 or 3, then default, it's a base of 10. Okay. The reason for that is because most of us have 10 fingers, 10 toes. We count by tens. Our number system is a base 10 system. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we count by another set of 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then another set of 10, and another set of 10, and another set of 10. So that's why our base, our standard base, is a base of 10. Okay. Okay. There are properties of logarithms, rules of logarithms. They're actually pretty easy to remember if you remember your rules of exponent. So when I teach these rules of logarithms, I like to relate them to the rules of exponents, which we went over in the last section. So if I have log base b, where I have two things on the inside of my log being multiplied, it's just like for exponential functions where I have a base and I am multiplying two things with the same base, right? I actually get to separate them by adding them. So same thing here. I can separate this into two logs by adding them. So we can write this as log base b of n plus log base b of n. So when I have two things being multiplied on the inside, I can separate them as addition. Okay. So the analogous rule for exponential functions is I have base b to m times base b times n, right? M times n. I can rewrite that as m plus n, right? So same style rule. Two bases being multiplied, right? Something being multiplied breaks down to addition. Okay. In fact, if I wanted to verify this form, I would take the logarithm of both sides here in order to verify that it was the same thing. Okay. Log base b of m over n. So we know for exponents, if I have b to the m over b to the n, that it turns into subtraction. So for logarithms, it'll be the same thing. I will subtract two separate logarithms, one with m on the inside and one with n on the inside. So the analogous term for the exponential functions is, as I said, b over m, or b to the m over b to the n, and then you subtract those powers, right? Okay. I'm sure you can figure out what this is going to be, right? So m to the p is going to be p log times m. The analogous rule is when I have b to the m raised to the power of p, I just multiply those two things. So this p gets to move down and just multiply my logarithm. Here, when I have log base b to b, that is going to be 1. Okay. If I have b raised to the log b of m, log base b of b, say that one time, b raised to the power of log base b of m. Basically what happens is that the b's and the log base b cancels, and I'm left with whatever's on the inside. Okay. So if you ever have a base raised to a power that is a logarithm that has the same base, they just cancel each other out. Okay. So for application problems, what we do a lot, like I said really briefly here, is take the logarithm of both sides. Okay. For an application problem, a word problem, generally when I need to use this is when I'm given an output value and they're asking us what input makes that output happen. Okay. So something like, if you invest some money that earns interest at blank %, right? How much money will you have after 5 years? Well, that's easy. You make an exponential function like in the last section, and you would just plug in 5 and you'll know how much money, right? That's an exponential function. But if they say something like, how much money, how long will it take for you to make $1 million money? How long will it take for you to make $1 million? That's an inverse. I'm given an output and they're asking me how long until that's going to happen. So then I would use an inverse function, right? I would use the logarithm, right? So example, how long until we have this much money? So things that look like that, right? They're asking us basically for an input value, right? That's when we're going to use a logarithm. Okay. So when we're solving exponential and logarithmic problems, we generally want to have 4 decimals of accuracy. Okay. If I want more decimals of accuracy, then I'll say. If I want less decimal points of accuracy, then I'll say that. 4 decimal places of accuracy means you have your decimal point and then 4 numbers after. Okay. I haven't really talked about error, round off error yet in this video series, but in my pre-calculus at the beginning we talk about error a lot. It's very important that we avoid round off error as much as possible, which means that you want to use, if I say I want something to 4 decimal places of accuracy, that does not mean you cut off at 4 decimal places every time you do a calculation. That means you keep as much information as possible throughout the entirety of the problem until the final step, and then you round to your 4th decimal place. Okay, so you do not just keep 4 decimals the whole time, because that will not be 4 decimal places. That'll be more like 3 decimal places or 2 decimal places of accuracy, and you'll end up getting the wrong value. You need to keep as many decimal places as possible, or use exact values as long as possible, and then cut off at the end. Okay, so let's do an example. Okay, solve the following problems. So for A, we have 5 times 3 to the x minus 4 equals 3. I know everything except for the input. The input is the thing that I don't know, which means that if I'm solving for an input value here for this exponential function to make this a true statement, I will end up having to use logarithms. So just like regular equations, my goal is to isolate the unknown. So I'm going to undo PEMDAS, right? So instead of going addition, subtraction, multiplication, division, or I'm sorry, going the other way. Instead of going parentheses and then exponents and then multiplication, division, and then addition, subtraction, I go the opposite direction. I'm going to look for any addition or subtraction to undo first. So I have this minus this, so I'm going to undo it by adding, right? So I add to both sides. Okay. And then I'm going to undo the multiplication, which is the next thing when you go backwards along the PEMDAS line. So then I divide by 5. So I add 4, divide by 5, and I get my term that has the variable in it equaling something, everything else basically, okay? So now that I've isolated the term that has my variable, I can take the logarithm of both sides. So I'm not going to turn this into a log by saying log base 3 of 7/5, right? I don't want to do that because having a log of base 3 is weird. We want to have either a log of base e or base 10 because our calculators can do that very easily, and it's the standard basis. So what we're going to do is we're going to take log of both sides, right? Or natural log, it doesn't really matter which one, as long as both sides have the same base. So I'm going to say log of 3x and log of 7/5. Okay, so here I'm using base 10 because my calculator does that by default. All calculators that do logarithms do base 10 by default, so that's what we're going to use. Or I can use natural log because all calculators that do logarithms also do natural logs as well. So I'm going to just apply the rules. I am not going to separate this one. I'm going to keep this as 7/5. But this one I am going to separate, and I'm going to use that rule where that rule number 3 here. Okay. Where something to a power means you take the power and pull it to the outside. Okay. So I'm going to apply the rules of logarithms and isolate my x. So my x comes out. So now I have x times log 3 equals some other log. And if I want to isolate x, I just divide both sides by log 3. So this would be an exact answer. I will take this as a correct answer for problems like this always. Okay. At this point, I've used exact values the entire time. I did not plug in a decimal for this. I did not plug in a decimal for this. I used the exact values. If I want to find out around how much this is, I would plug this into my calculator to get my 4-point decimal approximation. Okay, so I use the exact values as long as possible, and then if I choose to, I will find the approximate decimal value here. Okay, so let's do another one. So here we have base e. So now when we take log of both sides, we want to use natural log. But before we take log of both sides, notice that I have the same base on both sides. So what I want to do is I want to get all the stuff that have x's on one side. And I can do that by dividing both sides by one of these e to the power of x's if I want to. Or I can go straight into taking the natural log of both sides. Either way is okay. So for this example, we're actually going to just take the natural log of both sides. So here I have natural log of e to the 3x. And I'm going to take the natural log of everything on the right hand side. Okay. My rules of exponents says that I can break this into two different things. My rules of exponent or logarithms, here says I can pull out the 3x. Okay. When I pull out the 3x, I'm left with natural log of e. That's log base e with e on the inside. That they cancel out. So that's why you see only a 3x over here. Over here, this separates into natural log of 4 plus natural log of e to the negative 2x plus 5. Here, same thing, this negative 2x plus 5 gets to pull down to the outside, and I'll be left with natural log of e, so those will cancel as well. Okay, so now I have this equation. The only natural log present is 4. This exponent comes down, this exponent came out, and now I can start to get all my x's on one side by adding 2x to both sides, and then finish out by dividing everything by 5. Okay, so that leaves me with a 1 and a 1/5 natural log 4. Now, as I said, and I can get my decimal approximation, right? So I used everything exactly. So as I said before, there's another way for me to start this. Okay, so let's say instead of natural logging everything at the beginning, I divide first. Okay, so I divide either by e to the 3x on both sides, or I divide by this e to the negative 2x plus 5 on both sides. It'll be easier to divide by this term because there's less going on. I also want to divide by 4. So notice that if I divide by e to the 3x on both sides, this will turn into 1. So I would also like to get all my constants to one side, right? And everything with an exponent on the other. So I'll also divide by 4. So this will become 1/4. And this side will just be e to the negative 2x plus 5 divided by e to the 3x. So from here, what I need to do is I need to simplify this. I have the same base, different powers. So I just subtract these two. So negative 2x plus 5 minus 3x. Okay, so now I have e to the negative 5x plus 5. Now I can take the natural log of both sides. So I have natural log 1/4, natural log of e to the negative 5x plus 5. So just like before, the negative 5x plus 5 comes out, and the natural log of e will cancel out because it's equal to 1. So to finish solving for x, I subtract 5 and then divide by negative 5. And I get almost the same thing that I had before. So you see I have 1 minus 1/5 natural log 1 over 4. Here I have 1 plus 1/5 natural log over 4. The difference is that this 4 versus this 1/4, 1/4 is 4 to the negative 1 power, right? So if this was 4 to the negative 1 power, and I pulled out, sorry, this is 4 to the negative 1 power. So if I applied this negative, it would turn this into a 4. So these are actually the same thing. If I plug these both into my calculator, I get the exact same value, right? And that's because the rules of logarithms and exponents, these are actually the same. So if I want to turn this into a plus, I would apply this as an exponent form. So I would just be kind of undoing the rule that we did here to here for this natural log part. Okay. So instead of taking the power and pulling it in, or I could write this as 4 to the negative 1 and apply that power to the outside, and it'll turn it positive, and the inside will be a 4. It's the same thing. Okay. So for our last one, this is a little bit different. So if you've noticed so far, we either had the same base, e and e, going on, or we had only one base. So now for this one, for C, we have two different bases, a 7 and a 10. So my goal is the same. I still want to get all the stuff with x's on the same side and all the stuff that does not have any x's on the other side. So I'll divide by 2 and divide by 7, or the other way around, I can divide by 3 and then divide by this 2 to the x, right? So either way, it doesn't really matter as long as I get everything over. So I move this 2 over with 3, and I move this 7 to the x over with this 2 to the x. And now we can apply our other rule of exponents, which says that if we have two things with the same exponent, even if they're different bases, we can just pull that out as a common exponent. Okay. So now I can take the log or natural log of both sides, right? Which makes this x come out to the outside. Then to isolate the x, I divide both sides by log 2 over 7. Again, I have an exact value, right? And then if I want to get a decimal approximation, I plug this in, and then I can get my 4 value, my 4 decimal point approximation. Okay. So obviously, one of the main uses of exponents and logarithms are word problems. Really, any of these functions are word problems, application problems. So let's go ahead and do one. Where we are creating our exponential function, and then we have to use our logarithms, right? So we have a town that was founded with 30,000 people. 5 years later, it has a population of 40,000. We're going to say that the population grows exponentially. How many years until the town doubles in size, right? So we basically have 2 points. We have an initial value of 30,000, so you can think of this as 0 and 30,000, and a secondary point of an input of 5 and an output of 40,000. So we can use this information to try to create our exponential function, right? So we find our yearly growth rate as 40,000. Our output is equal to my initial value times some growth rate that I don't know yet, times raised to the power of 5, because 5 is my input, right? So when I plug in 5, I get out 40,000. I know my starting value, but I don't know my growth rate. So that's what I need to find in order to finish having a formula that models this. So I'm basically going to solve for this b now. Okay, so in order to do that, first I need to isolate this b to the 5th. So I'll divide both sides by 30,000. So this will give me 4/3 equals b to the 5th. Okay. And then now if I want to figure out what this base is, I will take the 5th root of both sides. Okay, so I will take the 1/5 power of b and take the 1/5 power of 4/3. This is an exact value, so now I can plug this into my calculator and get a nice decimal approximation. Or I can use this exact value as I do my math, so that I have an exact value and find the decimal points later. Okay, so as you can see, I use 5 decimal points here, so it's more likely that I'll be accurate to 4 decimal points if I use an extra one for my final answer, right? So my growth rate is 5.92%. So I want to know when the population is going to double. So if I'm starting with 30,000, that means that I'll double at 60,000, right? My growth rate then is going to be 1.05922, okay? And I want to know what x makes this equal 60,000. So I'm going to do what I did before. I'm going to divide both sides by 30,000. So I'll get 2 equals my growth rate raised to the power of x. And then now I can't take the 1 over x root because that doesn't work. That only works when I have a value. I need to take the log of both sides. Okay, so I will log both sides. The x comes out to the outside, and in order to finish solving for log, I divide both sides by log 1.05922. Okay, plug that into my calculator, and I get approximately 12.0479. So I try to use values as exact as possible, so that I have 4 decimal points of accuracy. So it takes a little more than 12 years for the population to double for this town.